Hey folks, this is Navy Fish, and as promised, here's a video with not just one but actually two prototypes that I've written demonstrating some of the techniques described in this forum post. So without further ado, go full screen here. So here you go. Here is the first of our planets that we will be looking at, and actually in orbit around it is a second smaller planetoid. These two use the exact same algorithm for their terrain, for their coloring, so very similar. Now I hesitate to actually call this a planet renderer, and we'll see why in a little while. Or rather, it's not really a procedural terrain generating engine, because honestly, there is no level of detail taking place here. This is being rendered at one level of detail. As a result, if we try and make the planet much bigger or render it at a higher resolution, we're really going to start bogging things down because we're trying to submit all of that all at once. So we can get in here, and it's somewhat detailed, but not nearly the level of detail you would want for a life-size planet. The bigger we make the planet, the lower overall we'd have to make the resolution. So that's why level of detail is so critical. Ideally, as I would zoom in here, more and more geometry would fill in, and over off there in the distance at that peak, that distant terrain would replace itself with a lower resolution or lower poly count version of itself. And you kind of balance the load on your graphics card. But we're not doing that here. So it's not really a true procedural terrain engine in that sense. It'll render this one size of planet, but that's about it. But that's not why I made this. This prototype was actually to look at transform feedback, which is how I am generating this planet. So if you're not familiar with the transform feedback, basically 100% of the terrain information is being produced and actually remaining on the graphics card. The CPU has nothing to do with the development of this terrain. So much so, actually, to its detriment, that it doesn't know where the terrain is. So it has no way of stopping me from flying through this. To solve for that, we have to do something else, and we'll actually talk about that with the next prototype. But back to the point, all of the terrain data is being generated on the graphics card. So the way that works is this planet is a quad sphere, as mentioned in the post. So it's a cube whose vertices we then normalize, which basically turns it into a sphere. Now from there, we feed each one of those vertices, well, the position of each of those vertices, into, oh, look at that. That's a cool little artifact. Yeah, it's a prototype. Anyway, so we feed each one of the vertices positions into a noise function that's located on the graphics card, and it spits out a height for that vertex. We then we actually save that height data, and then when we go back to draw that particular vertex, we the graphics card knows what vertex it's drawing, and so it calls up the height data that it calculated earlier associated with that particular vertex and displaces it from the center of the planet according to that height value. And so that's how you get terrain. That's how you get this variation in height or altitude above the surface. And again, 100% of that is being generated on the graphics card using a noise function. Now it's staying on the graphics card. We're using what's called transform feedback. I'm not sure if I mentioned that term before, but basically once you calculate that data, you save it into video RAM, and it remains there until you get rid of it. Here, I don't ever get rid of it. And that's because we are not doing any level of detail, as mentioned. So, if we were doing level of detail as more high resolution or high level of detail patches went off into the distance, we would throw away that higher resolution version of itself and replace it with a lower resolution version. Well, in that case, we would have to regenerate terrain, or probably a better example, as we zoomed in on some terrain, we'd be having to generate higher and higher levels of detail of that terrain. So we need more information that has to come from somewhere. That comes from the generation process. So that would be real-time terrain generation. We're not doing that here. At the very beginning of the demo, we know 100% of all the terrain that's ever going to be rendered, so we just render it up front, save it on the graphics card, and hold on to it. When we render it every single, I may have misspoke, we generate it at the beginning there. We render it every single frame, but it's only ever generated once. So that's actually something different that we'll look at in the next prototype. It does implement real-time generation and level of details, but again, this prototype was the first one I made. I wanted to test out some noise functions, but more importantly, play around with transform feedback and actually generating noise-based terrain on the graphics card. So before we move on to the next one, I'll point out one other big thing that we're doing here, and that is, the absence of any lighting. So as we kind of get close here, this green area just looks flat. There is no definition whatsoever. The terrain is actually somewhat varied in there, but you can't tell, and that's because there's no lighting. In order to light that terrain, we need what is called the normal. Now, I misspoke. We are lighting the terrain with an ambient term, but in order to light it with either a diffuse or a specular term, you need the normal of the polygon, which is basically the perpendicular direction of that polygon, and that's how you determine how the light's bouncing off of it and how much is reflecting and so on and so forth. So we don't have that information. As a result, things are very flatly shaded, and again, the color of these pixels is all based upon height. I think I may have mentioned that, but I didn't go into detail. Basically, every frame, each pixel looks at the vertices around it and asks them their altitude, which they know, and it interpolates, so it gets a sense of where it is, what its altitude value is, and then it simply looks up into a little table what color it should be based upon that. Now, it's per pixel shading or coloring. I hesitate to call it per pixel texturing per se, and that's because texturing implies that you're looking up like you're looking at an image of grass, for example, and then splatting some of that image onto the geometry. So that's texturing in a nutshell. We're not doing that. This is flat shading or just color picking. Now, if I was just doing that, it would be a very smooth transition between the shoreline, the tree line, so on and so forth. But you do see a little bit of perturbation that is being injected by some noise. So the height is actually uniform along that line, but what's happening is I'm telling the function that determines what color that terrain should be. I'm disturbing or distorting the data that goes into that ever so slightly, just adding some height or subtracting some height based upon a fairly high frequency noise function, and as a result, you get a little change. It introduces a bit of variation, but overall, very simple shading, very simple coloring, no lighting. So it's basic and it looks basic. So again, that wasn't the point of this prototype. It was to do transform feedback, and it did it somewhat successfully. So enough on the. Oh yes, one more element. This is not doing any occlusion culling. So basically, the entire planet is being submitted for rendering at every frame. I know from where I am above the terrain that a certain amount beyond the horizon is not visible. Here it's about half the planet, or the backside of the planet. But as I zoom in, only about 5%, maybe less, 1% of the planet is actually visible. Probably, here it's like 1% beyond the horizon. Regardless, we submit every other piece of geometry to the graphics card. There's some things it can do, like fast depth discard, I think it's called, I forget exactly, but basically if it's about to draw something that would end up behind another pixel and thus it would not get, its color would not contribute to the final image, then the graphics card can tell that ahead of time and skip out most of the rendering. But that doesn't save you. That saves you some, not a ton. Likewise, if I'm off screen like this, well, it's still submitting the entire planet. Now the graphics card has specialized hardware that can determine, okay, well, this polygon isn't on screen, so we're not going to run any further calculations on it, but it has to do that per polygon. So that's 16 million or something like that triangles that it has to make that decision about every frame. So again, camera-based occlusion detection would help alleviate some of that, and position-based occlusion detection would alleviate even more. I wouldn't even have to test the entire back half of the planet because I know it can't be seen. So those are some pretty critical features which just aren't in play here. All right, enough on this one. Let's move on to the next prototype. Now, this next prototype is a little more advanced in some ways, but it's also got a more narrow scope. Let's see. As we zoom in here, or as we move, you'll notice right off the bat that we've got a much more, I don't want to say realistic, but more complex looking terrain function. We are using what is called a rigid multifractal as the noise function. So a multifractal means that the inputs to the noise function themselves change over time, over distance, well, in this case over distance. And that, if it's tuned right, will give you large areas of plains and then areas of mountains where mountains clump together and so on and so forth. This isn't tuned very well, so that's just part of the nature of it. But that's a ridged multifractal, and the ridged part of it, you can see there are ridges. It adds this kind of fantasy realm, almost Alps if it was a little less extreme, but that's coming from an absolute value term in the noise function, and it creates these discontinuities effectively. So there you go. That's one thing, playing around with a new noise function. The other cool thing to notice here is, well, if I zoom out, you start to lose it in the fog here, but this is a flat plane. There is no sphere happening here, but it's an infinite flat plane. So I can just keep going and going and going and going, etc. And at the very edge of the visible horizon, I am generating a new terrain patch. Likewise, behind me, I'm throwing out the terrain that's behind me. So I'm only ever really rendering a fairly small amount of the world that's around the camera, and the rest of it just gets thrown away when it goes too far. So as a result, we are doing real-time terrain generation. That's a pretty big step. Additionally, we're doing level of detail. So I want you to focus on the horizon and look at specifically the transition between the snow and rock color, and boom, do you see that pop right there? You keep looking, and every once in a while you'll see a big shift. Well, it shouldn't be doing that. That's an oversight in my texturing algorithm. But what you're seeing there is the transition from one level of detail to the other. Now you may notice that the geometry doesn't look like it's popping. It basically stays the same. You might be able to tell if you have a keen eye, but for the most part the geometry remains the same. And that's the point of a level of detail algorithm, that it swaps the lower resolution geometry for a higher resolution geometry before you would see the difference. Now again, oversight in the texturing, and so my texture coordinates are shifting around a little bit, and so you see the textures move and distort, but anyway, there is level of detail taking place here. So again, what that means, we are using transform feedback. We are generating 100% of this geometry on the graphics card, and we're doing it real time. Every time the camera moves and reaches a certain threshold, we toss out some data and we regenerate some new data, so on and so forth, giving us this infinite terrain. Another interesting thing we're doing is, well, remember the last planet, you could just fly through it. Here, that's not the case. I can kind of climb it bounce off it, but I cannot get through it. And that is because the CPU actually does know a little bit about this terrain. So I'm going to turn on some boxes here. I told you I'm rendering this all on the graphics card, and that is true, or excuse me, generating this on the graphics card. But then, based upon where the camera is, and it obviously as it moves, that changes, I have the CPU request of the graphics card to send some data back to the CPU. So these bounding boxes actually are depicting what data the CPU knows about. So the CPU actually asks the graphics card, hey, some of that data you just generated, yeah, will you mind sending me a little bit of that? And then it can use that for a collision detection. Now, you could use it for more complex collision detection. I'm just doing, based on the camera height, don't let yourself get any lower than the terrain. It's very simple. But another interesting thing is these bounding boxes are being calculated based upon the highest feature in here. So right here, this peak, right at the very border, wow, is the highest feature in that terrain. Likewise, this peak, man, I'm getting a lot of edge cases. Let's go over here. And the way I'm able to do that, there you go, this highest peak is what's determining this bounding box. I'm actually scanning over all of this vertex data, and that's being done on the graphics card as well. Graphics cards are very good for massively parallel operations, so I'm able to basically look through every single vertex in there and see which one has the biggest height on the graphics card, and I do that at the time of generation. So when I submit, I do submit all of this data back to the CPU and requested, but it also sends back a single value saying, oh, and by the way, not only here's all the terrain data, but we've already figured out that the highest bit of data in this patch is, I don't know, 300 meters or whatever. And that's what the CPU uses to generate these bounding boxes. Those can be used for lots of things, to include more complex level of detail selection, so on and so forth. I won't go into all of that, and I'm not implementing any of it, so it's somewhat irrelevant. Okay, I am getting bogged down in the details, but there's a lot more to cover here, so let's turn these off, and let's now focus on the coloring. So in the last prototype, it was very flat shaded, very simple. Here, obviously, we've got a lot more variation, a lot more detail. That's because we're not just doing an altitude-based approach. We are including altitude, but more importantly, we're looking at the slope. Now, the astute, listener will understand that that implies we have to know or estimate at least the normal. So we'll get to that. That's a little that's a little foreshadowing there. But the slope of the terrain, aka how steep it is actually being used in the coloring calculations. So once the terrain is above a certain height, if the slope is steep enough, it's rock. The snow falls off the rock or whatever. And below that, it's snow. Even with that, however, we'd have a fairly smooth transition between the two textures. And so again, we are using some high frequency noise to perturb the inputs to that function. Actually, instead of using altitude as we were using last time, though, I'm using slope here. So I've just found it gives a little more natural effect, and you can imagine it's almost simulating, variations in the terrain at a very low level of detail, little boulders and stuff, which are hard for the snow to stick to, so on and so forth. So that is part of the lighting here, or excuse me, part of the coloring here. But the other part, which adds a huge amount of detail, is lighting. I kind of gave it away there. So you can see here these three ridges in the foreground. Those without lighting would be nearly impossible to see, because the altitude, it's against a similarly colored backdrop. In fact, these are all using the same snow texture. Well, it's not a texture, but we'll get there. The reason you have this clear difference is shading. There's actual light calculations taking place here. So as we kind of alluded to earlier, I am in fact calculating the normals, and that is also being done on the graphics card. So at the moment of terrain generation, not only do we go and figure out the terrain altitude, the maximum altitude, but we also scan back through it and calculate normals for every single vertex. And that allows us to do fun stuff like this. Oh yes, here is a simulated night and day cycle. So I'll slow that down, make it a little less trippy. So here you go. We got some nice shadowing at this sun angle. That is diffuse lighting. I do have specular lighting in here that's not, well, it's not turned on, but it's not really important. What diffuse lighting is basically the more direct light you're getting on a surface, the brighter it'll be. So here we have a very overhead light, so everything's reflecting. But as it comes more to an angle, in general there's less reflection. The bright side of the mountain is in the direction of the sun, or the light source. So the light source is up there. This side's bright, that side's dark. Sorry, probably a little confusing there, but now don't mistake this with shadowing. It's not the same, but it can give an approximation of shadowing. So that is diffuse lighting. Now another thing that the normals give me are a bit more texture. So this snow is actually just one color. It's just the white color of the snow. But you see what looks like a little texture. That's not a texture. It is actual. That is a perturbation using a very high frequency noise of the normal. So that is a lighting effect right there. Again, picture the snow having little wrinkles and rumples in it. I don't know, whatever you want to call it. And so the light is reflecting off it at different angles. And you can tell that this is being caused by lighting and not by texturing, because when we put a very direct overhead light, you almost entirely lose that effect. It kind of gets washed out. But then as the light becomes more shallow, you can see it being a predominant factor here in the terrain. Alright, so I have given you much more than I intended to. I hope you haven't gotten too bored listening to this, but I love talking about this. I love coding this stuff. So if you have an interest in it, and I assume you do because you're watching this video, and you have any questions, by all means feel free to post in this thread. I would love to talk about it, answer some questions, get you moving in the right direction, whatever you want. So I'll leave you there. Again, this is Navy Fish. Thanks for watching. I had a lot of fun making this video and sharing it with you, and hope to talk to you again soon. Take care now. Bye.